Assalamualaikum, my name is Muhammad Zakwan Ismail bin Esmar, leader of Group 4. In this video, me and my team will present regarding the digital electronics project that we are assigned. We will be explaining the stages of how we design our own FSM sequence as well as observing parallel in-shift registers using JK flip-flop by running a simulation.
Good morning, everyone. My name is Faizrul Aziz bin Fakrul Razi. Matrix number is DAE21203. Today, I will be walking you through the design and logic formulation for our finite state machine, or FSM, which we ultimately simulated using Tinkercad. Starting with stage 1, the very first step was defining the specific counting sequence for our project. Our sequence is divided into two parts. It initializes through 3 transient states, starting at 0, jumping to 5, and then to 7. Once the sequence reaches 7, it drops into our main continuous loop. It goes to 1, 2, 4, 6, 3, and then repeats by jumping back to 1. This specific repeating loop dictates the entire logic design of our circuit. Moving to stage 2, we needed to translate that visual sequence into raw data by building an excitation table. To do this, we use the standard JK flip-flop transition rules, which you can see highlighted. This reference table tells us exactly what signals the J and K pins need to receive to force a flip-flop to change its state, whether that is holding a 0, toggling to a 1, or taking a don't care condition, which is the X. We mapped out every single present state from our sequence and paired it with its required next state. By applying the JK transition rules to our 3 flip-flops, which we labeled QC, QB, and QA, we successfully filled out the exact binary inputs required for every step of the sequence. Finally, in stage 3, we took the raw binary data from our excitation table and plotted it into Carnot's maps to extract our simplified Boolean equations. For the first K map, which is the FFC maps, by grouping the active ones with the don't care X conditions, we isolated the most efficient logic gates for flip-flop C. The map simplified down to wires JC equals to QA bar and KC equals to QB. Equation serves as the exact wiring blueprint that we use to physically build the circuit on our Tinkercad breadboard. Thank you.
This brings us to page 6, the simulation phase. Before wiring anything physically, we needed to prove that our logic actually worked in practice. First, we took our 6 Boolean equations and built a prototype in Logisim. This software let us visualize and construct the circuit using clean logic gates to verify our truth table and ensure our continuous loop transitions exactly as designed. Once confirmed, we use that Logisim schematic as our base blueprint for Tinkercad. Here, we translated theoretical gates into physical integrated circuits using standard 7400 series chips. This step required careful attention to detail mapping, precise pinouts, managing power lines, and routing the clock signal so the flip-flops triggered simultaneously. Ultimately, our Tinkercad simulation successfully outputs our exact binary sequence via the LEDs, proving our design is a complete success.
Next, let's move to the next touch, which is parallel in-shift registers using 7476 JK flip-flop simulation using Logisim. So for this task, we need to develop a 4-bit recirculating shift register simulation in Logisim. We also verified the asynchronous clear and parallel load functions to establish baseline states. After that, we observe shift-right operations, tracking the bit patterns as they cycle through the system synchronously with the clock pass. For this circuit, we also made a clear component by using pin and inverter because in Logisim there's no direct component to use as a clear component.
Hello, my name is Amin Mirza Shamim bin Mustafa Kamal, matrix number AA2500064. Now, let's examine the empirical result of our Logisim simulations. This 15-step truth table fully validates our 4-bit recirculating shift register. First, we verified our asynchronous controls, asserting the active low clear instantly resets all output to 000 regardless of the clock, while the parallel load successfully overrides the system to initialize custom bit patterns. Under synchronous clock pulses, our data tracks reveal two critical engineering insights. First, recirculation periodicity. A loaded bit pattern cycles through the register feedback loop and returns to its original position precisely every 4 clock pulses. Second, shift integrity. Multi-bit patterns such as the adjacent active bit loaded on line 10 propagates seamlessly without timing hazard or data loss. Ultimately, this data confirms our 7476 JK flip-flop logic design is mathematically and functionally 100% verified. Thank you.